Alright, in this video we study this type of differential equations, that is homogeneous linear differential equations with constant coefficients. Constant coefficients means this: the coefficients of derivatives of y, they are not functions of x but constants. This type of differential equations have many practical applications, including the equation of motion of the harmonic oscillator, such as this one we have seen before. So second derivative and constant here, and the function itself. So this is, in this case, this is second order, and there's no first order term and zeroth order term here. And so previously we just show the solution of this to be y equal to some constant times cosine of omega x plus some constant of sine omega x. But we didn't show how we can derive this solution starting from this equation. In this video, we study how. So let's start. Okay, so first let us define this differential operator as we have done before. This d to the power of n. Of course, d is the differential operator that represents differentiation with respect to x, plus an minus 1, dn minus 1, and so on, and a1 d plus a0. Then this original differential equation becomes simply e times y equal to 0. Next, instead of this differential operator, let's consider this polynomial that looks much the same, but instead of differential operator d, we have a variable t here. So t to the power of n, an minus 1, t to the power of n minus 1, and so on. a1 times t plus a0. So this is a polynomial of t. And if we substitute d, this t with, replace this t with d, differential operator, then we have this differential operator e. Just replace this t with d. So that means this differential equation becomes f of d applied to y equal to 0. So this is just rewriting the same equation, so there's nothing new here, but this will help. Well, at this point, let's make a little bit of detour to study some property of polynomial functions in general. First, we define the notion of relatively prime or coprime of polynomials. So suppose we have two polynomials, f1 of t and f2 of t. So we say they are relatively prime or coprime if f1 of t equals to 0 and f2 of t equal to 0 do not share any solutions, do not have common solutions. Well, it's not just in real number solutions, but complex solutions. Okay? As we will see later, any polynomial equations are guaranteed to have complex solutions. They always have complex solutions. Well, it may happen to be real, but within complex solutions, and there is no polynomial functions that do not have any solutions within complex numbers. So anyway, so if two polynomials do not share any common solutions, then they are relatively prime or co-prime. Now let us introduce a little lemma. So if we have two polynomials that are co-prime, then there exists some polynomials, let's say g1 of t and g2 of t, so polynomials, such that f1 of t times g1 of t plus f2 of t plus g2 of t equal to, not 0, it's 1. It's 1, and vice versa. So it's if and only if statement. We do not give the proof of this lemma, but maybe you can find the proof in some algebra book or abstract algebra book. Let's see a few examples. For example, if f1 of t is equal to t minus 1 and f2 of t is equal to t minus 2. Of course, these two polynomials are co-prime because t minus 1 equal to 0 means t equal to 1, and t minus 2 equal to 0 means t equal to 2, and they do not, the solutions are different, so they are co-prime. Okay, in this case, if we set g1 of t equal to 1 and g2 of t is equal to negative 1, then we have g1 t times f1 of t plus g2 of t times f2 of t equal to 0. Right? So it's just 1 times this and negative 1 times this. So that's, if you do that, you get 1. So this holds. Okay, next, let's see a less trivial example. So let's see if 1 of t is equal to t cubed minus t squared plus 2t plus 3, and f2 is t squared plus 1. So are they co-prime or not? To see that, we can apply the Euclidean algorithm. So that is, so this is the polynomial of the third order, second order here. So let's divide f1 by f2. So this will be something, quotient f2 plus the remainder. So let's find out. So let's see, t cubed minus t squared plus 2t plus 3. Let's divide this by t squared plus 1. So that's t cubed, and this is t. So negative 3 t squared here plus t plus 3. So that will be negative 3. And negative 3 here. So t plus 6. So the quotient is t minus 3, this one. And the remainder is this one, t plus 6. And next, let's divide f2 by the remainder. So that will give us some quotient and t plus 6 and some remainder. Okay, so t squared plus 1 divided by t plus 6. So let's see, let's put this to here. T squared and 60 minus 60, and erase this one, and minus 6, and minus 36, so 37. Okay, so the quotient is t minus 6, and the remainder is 37. Now, this remainder is a constant. It's not a, it doesn't include t. So the next one, if we divide this t plus 6 by 37, so the remainder is 0, and this quotient is just t plus 6 over 37. So that means this is the greatest common divisor of these two polynomials. Actually, we can always divide this constant by 37 to have the leading term of 1. So in that case, the greatest common divisor is just 1. Okay, so that means these two polynomials are actually coprime. Since they are coprime, there should be some polynomials g1 and g2 satisfying this equation. So how do we find these polynomials? For that, let's start from, let's see, here. Okay, so 37 is equal to this one, f2 minus t minus 6, t plus 6. Okay, so this is equal to this minus this. And now next, this one, t minus 6 was the remainder here. So this is equal to f1 minus this thing. Okay, so this is f2 and t minus 6, and f1 minus, what was it, t minus 3 times f2. Okay, so let's expand this, and this times this minus t minus 6 f1, and this times this, so negative sign, and t minus 6 times t minus 3 is t squared minus 9t plus 18 plus 1 from here. So that would be t squared minus 9t plus 19 f2 of t. So let's divide both sides by 37. Then we have 1 equals to negative t minus 6 over 37 times f1, and this polynomial here, 19 over 37 f2. So this is g1 and this is g2. So as the lemma claims, we have found these polynomials. Okay, next, what happens if two polynomials are not coprime? For example, let's say f1 of t is t cubed minus 8, and f2 of t is, let's say, t squared minus 4t plus 4. So the first one can be factorized as this. T minus 2, t squared plus 2t plus 4. And this one is t minus 2 squared. So they have t minus 2 in common. So they are not coprime. Okay. So suppose we do have two polynomials, g1 and g2, such that this equation holds. Okay, suppose there exists G1 and G2 such that this holds. Okay, then what happens? Then the left-hand side is divisible by t minus 1, t minus 2. Divisible by t minus 2 because this contains t minus 2 and wait a minute, f1 contains t minus 2 and f2 contains t minus 2. So these two terms are both divisible by t minus 2. That means the whole left-hand side is divisible by t minus 2, but right-hand side is not, which is a contradiction. Therefore, there are no such polynomials as g1 and g2 satisfying this equation. All right, now we can go back to the discussion of differential equations. So let's see, if we have two polynomials, and that are co-prime, okay, then let's see, if we have differential equations and let y1 y1 be the solution of this differential equation. So f1 of d applied to y1 is equal to 0, and f2 d y2 equal to 0. So suppose we have these solutions, y1 and y2. Okay, then consider this polynomial, ft equals to f1 of t times f2 of t. So that means ft, this polynomial, this is another polynomial that is a composite of f1 and f2. Then, now we consider another differential equation, fd of y equal to 0. Then the question is, what is the solution of this differential equation? All right, now here is the theorem. Let's say this is star, and y is a solution of this differential equation if and only if y is the sum of y1 and y2, where y1 is the solution of this and y2 is the solution of this. Okay, let's prove this. First, prove only if part. So suppose y is the solution of this equation. Okay, then since f1 and f2 are coprime, so there exist some polynomials g1 and g2 such that g1, f1, and g2 and f2 is equal to 1. So at this point, let's define y1 as, let's see, g2, f2, let's see, it's not t, but let's put the differential operator here, and f2 of dy. Okay, so this y is the solution of this differential equation. Okay, and similarly, let's define y2 as g1 of d and f1 of d applied to y. Okay, so if we define like this, then if we substitute t in this equation by d, we have g1 of d, f1, and g2 of d, f2 of d equal to 1, right? So if we apply this both sides to y, then we have y here, and 1 times y is just y, right? And this one, as we have defined here, is y1, and this one is y2. Therefore, y is equal to y1 plus y2. And the next thing we need to show is that this y1 is actually the solution of this differential equation, and y2 is the solution of this equation. Okay, so let's apply f1 of d to y1. Okay, then f1, by the definition of f1, we have this. No, I mean definition of y1, we have g2 d and f2 d of y. Okay, so this part came from the definition. And now these differential operators are commutative, so we can just swap the order. And we have what? F1 and F2, and let's see, I think we should put G2 first. Okay, so we G2 of D here and Y. Okay, but this one is F D by the definition. Okay, we are assuming that this polynomial F can be factorized in this way. So that's this, and but this one, by this assumption, it's 0. So therefore, y1 is a solution of f1 d y equal to 0. Okay, and similarly, and y2 we can prove in the same way. Y2 is a solution of f2 of d y equal to 0. So we are done with the only if part. Okay, next, so if part. So suppose y is given as the sum of y1 and y2, where y1 is the solution of this differential equation, and y2 is the solution of this equation. Okay. Then let's see, f d of y is equal to f d of y1 plus y2, and f d is f1 times f2 d, y1 and y2, and let's distribute this, and we can always swap the order of differential operators. So for the first one, let's say f2 times f1 times y plus f1 and f2 y2. But by the assumption this and this is 0 and this is 0. So therefore this is 0. Therefore y is a solution of this differential equation. F of d applied to y equal to 0. And we are done. Okay, let's see an example. Consider this differential equation. If y double prime minus 3y prime plus 2y equal to 0. So this is a homogeneous linear differential equation with constant coefficients. And this equation can be rewritten in this form. So d is the differential operator, and d squared 3d plus 2 applied to y equal to 0. So let's factorize this differential operator. So we have d minus 1 and d minus 2, y equal to 0. So what we need to do is to solve these two differential equations, this one and this one, which are considerably easier than the original one, this one. And from this, we can immediately solve this. So that's why, let's say y1 equal to some constant, let's say c1, exponential of x. So if you get used to it, it's immediate, okay? y2, let's say constant is c2, exponential of 2x. So the general solution of this original differential equation is given as the sum of these two solutions. So c1 exponential of x, c2 exponential of 2x, and we're done. Well, you should check if this solution indeed satisfies this equation. So just differentiate once and twice and substitute these into these terms, and you'll see. Before dealing with more general homogeneous linear differential equations with constant coefficients, let us again make another detour to study some algebra. That is the fundamental theorem of algebra. Theorem of algebra. That is this. Here we only consider a polynomial of real coefficients, okay? Consider a n x to the power of n and a n minus 1 x to the power of n minus 1 and so on. A1 x plus a 0 equal to 0 and a0, a1 and so on. They are all real, and we assume that an, this leading term, the coefficient, is not 0. Okay. This fundamental theorem of algebra says that this equation has exactly n solutions, possibly redundant. So some of the solutions may be the same value, possibly redundant. And solutions in complex numbers. Okay, so some of the solutions may not be real but complex, but nothing other than real or complex numbers. So what this means, this sounds a little bit abstract, but what this means is very simple. So what that means is that we can factorize this polynomial in this form. So an x minus alpha 1 to the power of, let's say, m1, and x minus alpha 2 to the power of m2, and so on, and x minus alpha, let's say, l to the power of ml. So we can always factorize in this form, and this an is the same as this an, and alpha 1, alpha 2, alpha l. So these values are complex constants, and m1, m2, and so on, they are positive integers or natural numbers. And exactly n solutions means that this m1 plus m2 plus and so on plus ml is equal to n. So this m1 and so on, m2, these are the redundancy of each solution. And we do not prove this theorem here, but all you need to know at this point is that it is always possible to factorize any polynomial of real coefficients in this form. Actually, the coefficient can be complex numbers, and this theorem still holds, but that's not the case we are interested in here. We only consider real coefficients. By the way, here's a little quiz for you. If alpha, let's say, if alpha complex number is a solution of this equation, then its complex conjugate is also a solution. I mean, given that the coefficient, all the coefficients here are real numbers, okay? If that's the case, then we always have complex conjugates as solutions. And you should prove that. Now, here's a theorem. Okay, let f of t be this polynomial, t minus alpha to the power of m. And alpha is a complex number, and m is a natural number. Okay, and the solution of this differential equation, so d is a differential operator, is given by this form, c0 exponential of alpha x and c1 x exponential of alpha x and so on, and cm minus 1 and x to the power of m minus 1 e to the power of alpha x. And here, these coefficients, c0, c1, and so on, they are complex numbers, complex constants. Okay, let's prove this theorem. First of all, let h of x be any function, any differentiable function of x. Okay, then apply this operator, differential operator d minus alpha constant, h of x and exponential of alpha x. So we just distribute this here and here. We have this h of x alpha e alpha x minus alpha. So this is just multiplication of a constant, alpha x. And here we mean we apply this differential operator to this product. Okay, so we apply the product rule. So that gives us h prime e alpha x, and differentiate this part, and we have alpha h x exponential of alpha x minus alpha h of x exponential of alpha x, and this cancel. So we have h prime alpha x. Now, so this is equal to this. And if we apply this operator again to the both sides of this equation, then we have d on the left-hand side, we have d minus alpha squared h of x exponential of alpha x. But here we have this. Okay, here h is an arbitrary function. So h prime is again an arbitrary function. So we can do the same thing as this one, but h replaced with h prime, and we have h double prime of x and alpha x. Okay, so this 2 and this 2. Okay, let's write in similar form like this. So if this is squared and this is second derivative. And if we continue this, let's say k times h of x exponential of alpha x, we have, if you want to be a little bit more rigorous, then you can use the mathematical induction to prove this. Okay, but I think this is clear enough. So this is h. So in general, we have this. For k is any positive integer. Okay, but if h is a polynomial function, of degree less than m, then we have d minus alpha to the power of m applied to h of x exponential of alpha x equal to 0, because the degree is less than m. So if you differentiate m times, then the derivative, so mth derivative of h is 0, right? So therefore this should be 0. Okay, so what this means is that the function of this form is a solution. So let's say this is star. So therefore this is a solution. So far what we have shown is that this form of the solution is sufficient to satisfy this differential equation. Okay, but next we show that the solution of this differential equation is necessarily of this form. Okay, so suppose y is a solution of f d equal to y. Okay, then let's define h of x as y of x times exponential of negative alpha x. So this y of x is this solution, okay? Then so multiplying exponential of alpha x to both sides here, we have h of x exponential of alpha x. Okay, so this means f d of y gives us, so from the former argument, from this, now this h can be any function, right? So the same thing applies. So this fd is the mth power of d minus alpha. So this results in h, the mth derivative of h times exponential of alpha x. Okay, but from the assumption y is the solution of this equation, so this must be equal to 0. Okay, so that means h of x must be a polynomial, is a polynomial of degree at most of m minus 1, because if it's degree of at least m, then it's not equal, it won't be equal to 0. So it must be at most this degree. Therefore, this the solution must be of this form. Okay, so we are done, and let's consider an example. Okay, now we can deal with the harmonic oscillator. So m, second derivative of x with respect to time, kx. So this is a very basic physics problem where x is the coordinate of a particle, mass point actually. So we have a mass point, let's say this one, with mass m, that's in maybe in kilogram, and it's bound with a spring to the at the origin. So this is x, and the spring constant is k. Okay, and if x goes to the positive side, then this particle feels the force in the opposite direction. So therefore this is minus sign. So this will oscillate around the origin like this. Okay. So how we can solve this equation? First, let's divide both sides by m. So we have this. Let's move this and define this k over m, which is a positive number, as omega squared. So we have, so this is second derivative. So that will give us d squared, so plus omega squared x equal to 0. Okay, so let's factorize this one. D minus I omega, d plus I omega x equal to 0, where I is the imaginary unit. Okay, so square root of -1. So according to what we have learned so far, we can solve this equation by solving two differential equations and combine the solutions. So this one and this one. These equations involve imaginary numbers, but we don't have to worry about it. We can just treat this imaginary unit as just another constant which happens to be -1 when squared. That's all. So if we solve the first one, from the first one we have, so this is immediate, x is, let's say x1 is equal to some constant exponential of positive omega t. Okay, here the independent variable is t, time t. From 2 we have the solution, let's say c2, which is a constant, and negative I omega t. Therefore, the solution is the linear combination of these two. So C1 I omega t plus C2 exponential of negative I omega t. So that's the solution. Okay, x is a function of time. So here it is. And it may seem a little bit strange. We have complex numbers here and here, and C1 and C2 can be complex numbers. But we are dealing with a physics problem where everything is measured in real numbers. Okay, this x must be some length or distance from the origin. It's the coordinate, so it must be real. And k is a spring constant, so it's a real number, and mass is of course real number. Everything is real, but the solution is possibly a complex number. So this coordinate can be a complex number. It's a strange thing. But actually, this can be made real. Okay, so if we use the Euler's formula, this complex exponential of I something can be expressed in terms of sines and cosines, right? So let's see, C1, so this is cosine omega t plus I sine omega t. And C2, cosine omega t minus I sine omega t. So we have this real part and imaginary part, and so let's solve them out. And we have C1 plus C2 cosine and C1 I times C1 minus C2 and sine omega t. Okay, so this is a real function and this is a real function. So if x of t is a real function, then the coefficients here and here should be real. Okay, so c1 plus c2 should be real, and I times c1 minus c2 should be real. Okay, so we cannot just choose the values of C1 and C2 independently because they have to satisfy these constraints. So these constraints can be easily satisfied if C1 is the complex conjugate of C2 and or vice versa. Okay, in that case, this is just real number. You know, the imaginary parts will cancel out. And here, C1 minus C2 should be purely imaginary. So multiplying by the imaginary unit will make it real. Okay, so this and this are real numbers in this case. So now we just define this this as A, let's say, and this as B. Then we have x of t is equal to A cosine omega t and B sine omega t, where A and B are real numbers. Now everything is real and we are satisfied. Here's another example. Consider this differential equation. So third derivative here and second derivative. The first derivative minus 3y equal to 0. So here we consider this polynomial. Let's say f of t, t cubed plus t squared plus t minus 3. And so if we use this polynomial, then this equation can be expressed as just f of d y equal to 0. So we want to solve this one. To solve this, we first factorize this. Okay. So how can we factorize this? If we put t equal to 1, then this is 1, 1, 1 minus 3, which is 0. So t equal to 1 is one of the solutions. So we can factorize by t minus 1. So, and if you do that, let's do it here. And okay, let's see. T minus 3, and so t minus 1 should be one of the factors, so t squared and t squared here, and 2t squared plus t minus 3 and 2t and minus 2t. Okay, that's it. 3 t minus 3, so that's 3. 3t minus 3, so that's 0. Okay, so this is t minus 1 and t squared plus 2t plus 3. So this one so can be factorized as this one. So t minus alpha and t minus alpha conjugate, where alpha and alpha should be, let's say, so solve this quadratic equation, t squared plus 2t plus 3 equal to 0. Solving this, we have, let's see, minus 1 plus square root of 1 minus 3. So that's so that's negative 1 and I square root of 2. And alpha conjugate is negative 1 minus I square root of 2. Okay, so we need to solve three first order differential equations. This one, this one, this one. So by solving this, we have y, let's say y1 equals to, let's see, c exponential of x. And by solving this, c1, y2, c2 exponential of alpha x, and d minus alpha bar. From here we have c3 exponential of negative alpha, wait a minute, it's just alpha bar x. Okay, so we have these three solutions, and the general solution should be the sum of them. So C1 and C2 and C3. Now let's write these alphas more explicitly, and we have this and negative 1 plus I square root of 2x, and C2 C3 exponential of negative 1 minus I square root of 2x. Okay, now this exponential can be split into this real part and the imaginary part, and we have let's see, c2 exponential of negative x times, let's see, let's factorize the same terms into 1, and we have exponential of negative x and c2, and exponential of I square root of x and c3 exponential of negative I square root of 2x. And as we have done before, in the case of the harmonic oscillator, we can make this into purely real. So in terms of cosine and sine. So if we just expand this using the Euler's formula and get rid of these I terms, that will be a cosine square root of 2x and b sine square root of 2x. So this should be the the general solution of this equation. Basically, as we have seen in all of these examples, for homogeneous linear differential equations with constant coefficients, we only have two types of solutions. That is exponential function or oscillating sine and cosine functions. Or in other words, we have exponential of some pure imaginary exponent. Okay, so all the solutions are just some kind of combination of these two different types of solutions. And that's all we have. Okay, that's it for this video, and see you later.